Hello, everyone. This is the lecture for section 2.6, Moments and Center of Mass. So this is going to be another section in our study of Calc 2 and our study of integrals that'll have some stuff that comes from specifically a first semester physics course. Okay, in particular, the definition of moments and center of mass and equilibrium. Okay. Um, so just keep an eye on that we're trying to use this to study integrals. Okay. Um, so yeah, let's just go ahead and get started. So there's a couple definitions that I need to bring up before we start moving into the calculus that we require, right? So the first definition is the idea of a moment. Okay, suppose that you have a mass m that's an x distance away from the origin, and then the moment for this object, it's m times x. It's just the mass times the distance, and that is it. Okay. Um, we say that a system of masses is at equilibrium. Okay, and what we mean by that is that it is balanced. That if you you have this system that's perfectly balanced, it's not teeter-tottering in any direction. Okay, we say that it is in equilibrium if the sum of the moments is equal to zero. So if we add up all these moments and they add up to zero, then our system is fully balanced. We say that it's at equilibrium. Okay. And it is at equilibrium over the fulcrum point or the balance point of the system. Okay. So essentially, this is where you're going to put your finger or where you're going to put your pencil, right? So that the entire system that we're looking at is completely balanced. Okay. So that's what we're looking at in this section right here. We're looking at finding balancing points. Okay, specifically in at least in our study, that's what we call the center of mass. Okay, so we're looking for balancing points, or the center of masses of objects. Okay, so let's go ahead and develop the idea of equilibrium really quick. So let's say I had two masses, m1 and m2, that are a fixed distance away, x1 and x2 away from the origin. And you know that they are in equilibrium, aka they are balanced, right? Okay, so what I'm going to do is I'm going to put down an x and a y axis, really small, not too big. I'm going to go right there. I'm going to put another one right here. Now that's good enough. Okay, so here's our origin, right? And suppose I had two masses, right? I'm going to put one right here. This is one mass. This is M1, a distance x1 away from the origin. Okay. And then I'm going to put another one over here, x2, a distance, sorry, M2, a distance x2 away from the origin, right? Okay. And suppose this is balanced, right? So we're saying that this is in equilibrium. So if we put our little fulcrum point right here, right, then we know for this system, M1, x1 plus M2, x2 has to be equal to 0. Okay, the sum of the moments is equal to 0. So we know this, right? That's what we're given from the statement above. We know that this system is in equilibrium, so we know that the sum of the moments is equal to 0. Okay, what we say here is this, that this right here is our x bar. This is going to be our this is going to be the location of our fulcrum, right? In this case, we know that our fulcrum is 0. Okay, because we said we're going to balance it over the origin, right? Okay, so now comes the next part of this entire thing. Suppose, right, that we know that the system is balanced. We know that the system is balanced, right? Suppose we just picked up the entire system and moved it a specific amount, right? So suppose we picked up our values, right? So this right here, I'm going to put the box over here. Suppose that's M1, right? And suppose this right here is our next box, right? M2, okay? Suppose we picked up our entirely balanced system and moved it completely over to the left a certain amount, right? And in this case, I'm going to move it a certain amount. Now it's not going to be zero, right? Here's my balancing point, right? And I moved it over X bar, okay? So I moved my entire system over. That's all I did, right? Then the distance here is going to be uh, the value of this X value right here is going to be X1 minus X bar. And then same thing over here. Uh, X1 minus, or sorry, X2 minus X bar, right? Since the system was already balanced way up here, right? This system must also be balanced, right? And it should be balanced at X bar, right? So since it was balanced, and then we have this statement for this system, right? We have M1 X1 minus X bar plus M2 X2 minus X bar is equal to 0. So we have this statement right here, essentially, right? Since the system was balanced before, and all we did was picked up the system and moved it over by an amount X bar, right? Then the sum of the moments should still be 0. It should be balanced. It should still be at equilibrium, okay? Now, let's say we want to try to solve for X bar, right? If we solved for X bar, we get this expression right here. This gives us the location of our fulcrum, the location of our balance point for this system. Okay. Now I want you guys to see what happened up here for the equation for X bar, right? It's going to be the sum of all the moments divided by the sum of the total mass. Okay. And that's how we find X bar. Is how we find the fulcrum with respect to the origin, right? So now to generalize the idea, let's say we had an entire system, right? MIXIs, a collection of masses a distance so and so away from the origin, right? It has a total mass. We can add up all the masses, right? And if we wanted to find the distance X bar such that this becomes an equilibrium, right? It's going to end up taking the same shape as this equation right here. Okay? That's it. That is it. So now let's go ahead and summarize that into two theorems. The first one's just going to be center of mass of objects on a line, and then we're going to move on to center of mass of objects in a plane. Okay, so the first one is the center of mass of objects on a line, right? So this is the thing that we were just doing up above, the generalization. Let a bunch of masses, right, be placed on a number line at distances that far away from the origin, right? The total mass is going to be the sum of all the little masses, right? Then the moment with respect to the system, for the system with respect to the origin is given by the sum of the mi times xi, right? And the center of mass is going to be given by the moments divided by the total mass. Okay, so that X bar is going to give us where we have to put our fulcrum, where we have to place our pencil, the balancing point for our system. Okay. All right, so now let's go ahead and do the two-dimensional one, which is the one from below it, okay? The center of mass of objects in a plane. So suppose you have a bunch of masses, right? And you place them on an XY plane, right? Just like before, it has a total mass, right? Then we can calculate the moments with respect to the x-axis and the moments with respect to the y-axis, right? And they're given by these equations. So keep an eye out for this. They work sort of opposite of what you think they would, right? The moments with respect to the x-axis are mi times yi, right? And the moments with respect to the y-axis is going to be mi times xi, right? And if you want to find the center of mass, then that is going to be x bar is equal to the moments with respect to the y divided by the total mass, and the moment or the center of mass with respect the y coordinate for the center of mass is going to be the moments with respect to the x-axis divided by the total mass. Okay, that sounded complicated, so I want to go ahead and do an example for everybody. Okay, so let's say we had this system right here. Okay, uh, I plopped down the points at least, right? So let me go ahead and get a shape going for everybody, kind of, maybe. It's a triangular shape, sort of, right? Bam, there we go. And I want to put the masses on here too. So mass one is 2 kilograms at 4 comma. So here, there's going to be 2 kilograms. At 4, it's going to be 4 kilograms. So I'm going to put 4 kilograms here. And then over here, it's going to be 5 kilograms, right? So what I want people to do here is, what I want to do right now is sort of give you guys a little bit of intuition here. I want to sort of guesstimate where my balancing point's going to be, right? So that's what we're looking for. That's what the center of mass is. We're looking for a balancing point, right? The fulcrum. Where would we need to put the fulcrum in order for this whole system to balance, right? So uh, the first thing I'm going to look at is this. Like I said, this is just intuition for now. We're about to solve it, right? 4 kilograms, 5 kilograms, those are close enough. So between these two, right, between those two weights, they should be, it should be pretty close to sort of smack dab in the middle between them, right? Maybe it's got to hug the 5 a little closer, the 5 kilogram thing a little closer, right? Um, but since these weights are about the same, not too much difference, right? Um, it's got to be somewhere halfway in between, right? The problem is this one. It's the 2 kilogram. Since the 2 kilogram is sort of a lot lighter than the other two, right? Then the 2 kilogram one should be really far away from my balancing point. Does that make sense? Because it's so much lighter, it needs to be farther away in order for it to balance our 4 and 5 kilogram masses, right? That are on the other end. Okay, so hopefully that makes sense for people. So my guess, right, and this is me just guesstimating, would be maybe that it might be somewhere around here. That's going to be our balancing point, right? So we're thinking that we need to put our pencil, right, or this is where we're going to need to put our finger in order for this entire system to balance out. Okay, so now let's go ahead and solve it. Okay, so the first thing that we need, according to above, right, we need the total mass, and then we need both the moments, the mx and the my. Okay, so the total mass is just like you think. You grab the two. There we go. 11 kilograms. That's the total mass of our system, right? All right, so now we need to do, there are two things we need to find. The my, right? The mass with respect to the y-axis. And in order to do that, that means we grab each and every one of the masses, right? Times its distance away from the x, times the x value of its coordinate. Okay, so this is going to be 2, -4, plus 4 times 4, plus 5 times 2. This is going to be -8, plus 16, plus 10. And all of this adds up to 18. Next one we need to find is the moments with respect to the x-axis. And that's going to be the exact same thing that we did for my, except we're going to be doing each one of the masses with the y coordinate. Right, so 2 times 1, plus 4 times 4, plus 5 times -1 is going to be 2 plus 16 minus 5, 13. Okay? So now all that's left is we need to find x bar. So x bar is going to be the mass or the moments with respect to the y-axis over the total mass. This is our 18 over 11 total mass. And if we do this, 1.6363 repeating. Y bar is the same, the moments with respect to the x-axis over the total mass, 13 over 11, and this is 1.1818 repeating. Okay, so now this right here is what's going to give us our x bar comma y bar, our center of mass for the whole thing, right? So let's go ahead and try to plop this down somewhere. So 1.6363, so that's for the x coordinate. So it's about 1.5 out, right? So 1.5, maybe a little more than that. And then the y is going to be 1 and a little less than a fifth. So 1.1/5, about right there would be my guess. So if we needed to balance this, if we needed to put our fulcrum somewhere, right? If we needed to put our finger down to where this shape right here is going to balance, it's going to be this point right here. This is our x bar comma y bar. Okay. All right. So what comes up next now is quick checks. Make sure you get these done. Okay. If you have any problems with them, come to the math lab. Come see me in my office hours, or come on the Friday times. Okay. So the next thing that we're going to move into is the center of mass of thin plates and laminas. So uh, unfortunately, we don't usually work with point masses, right? We work with materials, right? And these materials have different densities and different shapes, right? And we need to find center of masses for them. We need to find balancing points for some of these shapes. And that's what we're about to get into, right? We're going to be finding the center of masses of thin plates and laminas. Think of the way to think of this is, think of a a rando shaped uh, piece of aluminum foil, right? And we're trying to find the balancing point for all of it. That's what we're trying to do. Okay, that's what we're trying to do. So let's go ahead and go into the construction of what all of this entails. Yeah. So the first thing that I'm going to do, right, is I want to go ahead and do the total mass. What I'm going to do first is I'm going to do the total mass. Okay. So what I'm going to do is I'm going to plot down an x and a y axis. Okay. Leave yourself a little bit of room here. These drawings are going to get uh, pretty gnarly. So here's my x and y, okay? And I'm gonna just draw a function, okay? I'm gonna just draw a function. My good old standard curvy curve, okay? This is f of x, okay? Okay, so just like we did before, okay? Suppose, right, that I want a region bounded above by a function f of x, right, above the x-axis, over an interval AB. So I'm going to draw my A and my B. Okay. And we want to find, let me go ahead and draw this down right there. Okay. And suppose we want to find the center of mass of this region. So I'm talking about this entire region right here. All of this. We want to find, here's my region R, right? And we want to find the center of mass of this region R. So that's what the derivation is going to be. Okay. Oh, one more thing. that we need to sort of define here is that this region R has a constant density rho measured in mass per unit area. Okay, so what that means, this means really quickly, right, is that our density is measured in some mass divided by some area, right? So if we wanted a mass, right, it's going to be our rho times however much area there is. Okay, so I'm going to write this down here. We're going to need it in a second. Okay, so our big goal here, though, right? Our big goal here is we want to find this thing. We want to find the center of mass, x bar, y bar, for that pink region R. Okay, so let's go ahead and start our construction here. Okay, so I'm going to clear this out because I'm going to draw some stuff right below it. Okay, so to find what we're going to do first is we're going to construct for the total mass. So this is going to be for our total mass. Okay. So remember what we need for an X bar, Y bar, right? We need the total mass. We need the moments with respect to the X axis. And then we need the moments with respect to the Y axis. Okay. So first thing we're going to do, we're going to do for total mass. So just our M. That's all we're looking for here. Okay. We'll start off like we usually do. We have our from A to B, right? We're going to divvy this up into smaller partitions. Okay, so this is x0. This is going to be our xn. You actually write it appropriately. Equal xn, right? Since it's going to be a regular partition, we know that each one of these, right, is going to be a delta x, right, which is b minus a divided by n. Okay, nothing too wonko yet, right? So in order to find the mass, the total mass of our shape, okay, what we're going to do is we're going to use our rectangles again and find the area for one rectangle. Or sorry, the mass for one rectangle. So I'm going to go ahead and draw this like this, like that, right? And then we're going to just go ahead and say it's going to be about this tall. Okay, so you guys see this rectangle right here? Okay, we're going to try to find the mass of this one rectangle right here. Okay, so now this is where we're going to use this right here, this thing that we solved from up here. Okay, that our mass is going to be given by the rho, the density, right, times the area. And in this case, we are looking now for the area of this rectangle. Okay, so now we can go back to what we did before, right? So this is our xi plus 1, our xi rectangle. You guys remember that? Right? In order to find this area, right, it is defined by a random point xi star, whose height is f of xi star, right? Okay. And if you sort of run this out a little bit, the area for this, right, is going to be f of xi star, right? That's going to be the height times delta x. That is our width, right? And that is our height. Okay. So then therefore, right, the mass for this thing, our mi, right, is going to be equal to our rho times our area, right? And for this particular rectangle, it's going to be rho times f of xi star, times delta x. That is the mass for that particular rectangle. Okay, so that's where we get this right here. Okay, now this computation right here that I just highlighted is for one particular rectangle, right? And we have multiple rectangles uh, that go across from A to B, right? So the idea here is the total mass of this system is going to be the sum of all the little masses that are defined by each one of those rectangles. And that's going to be that expression right there, right? Which is the sum of all of these. All right. So that is this right here. I'm actually going to highlight it in green to show you guys to point this one out, because we're going to have three equations that I hope that we're going to end up turning into integrals in the not so far future. Okay. So this is going to be the expression for the total mass of our system. Okay. Okay. Let's move on to let's find the moments with respect to the x-axis. Okay. So again, I'm going to put down an x and a y axis here. Okay, so here's my wrong color. Let's do this right. I'm gonna put down an x-axis. Make sure I'm giving myself enough room for the y-axis, which is gonna come up in a little bit. And here's my other axis. Okay, so let's go ahead. It's gonna be the same exact, well, it's gonna be the same exact shape as above. Okay, so here's my f of x. Whoa. And I need, I'm doing the exact same shape from A to some point B, right? So dot, 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 dot. So what am I going to do here is I'm going to find the moments with respect to the x axis. Okay. Same thing as before. I'm going to go ahead, divide this up into smaller little pieces, right? Each one of these pieces is going to be my delta x, which is equal to the b minus a over n, right? This is still x of 0, x of n, same partition that we were working with up above, right? Okay. And I'm going to actually, you know what? I'm going to collapse that one down. No, move that point over a little bit more. There we go, right there. Okay. And I'm going to be using the same sort of partitions, right? And we're going to go through the same argument. And I want to find the moments with respect to the x-axis in this case, right? So with respect to the x-axis means I'm looking for something up and down. Okay. I'm looking for the balancing point with respect to the x-axis. Balancing point with respect to the x-axis. Okay. So I'm going to go ahead and call this one my xi plus 1. So I'm going to go ahead and draw this rectangle the best I can up to maybe about there. Down. So here's our rectangle, right? Okay. So the idea now is, like I said, we're trying to find the moments, right, with respect to the x-axis. Okay. And the moments with respect to the x-axis should be the sum of all the moments, right, for all of our little slivers, all of our little rectangles. Okay. So I'm going to go ahead and split it up again. using our partition. Okay. Now, the idea here is this is sort of like a crux of the argument. The entire region has a constant density. So that means that there's no more stuff in one part of our shape than any other part of our shape. Okay. So basically, the amount of material is evenly distributed along the entire thing. Does that make sense? Okay. Since that's the case, right, then that means that we should be able to, let me go ahead start here first. Uh, I have an xi star point that dictates the height for this thing, right? That's going to be f of xi star, right? So we're going to go ahead and try to find the moment for just this sliver right here, okay? Since the density is constant, right? There's no more material in our shape than in any other point, right? Then if we wanted to balance this pink sliver right here, right, we should be able to sort of set our pencil right across smack down the middle. Okay. In particular, we should be able to put our sort of our pencil right here. Okay. That point right there is given by xi star, comma, f of xi star divided by 2. That is our point there. Okay. So then that means that for this strip right here, right? I'm going to go ahead and do this. For this strip right here, our moment for this ith strip right here should be the mass of the ith strip times, and let me actually, I need to move this a bit farther north. There we go. The moment for this ith strip is going to be the mass for the ith strip times some distance, right? And we're doing this, like I said, a distance away from the x-axis, right? Okay. The mass of this strip, right? We figured that out from our previous section, right? It's going to be rho times f of xi star. Let me draw that a little nicer. Xi star times delta x, right? Now, we need the di. So what we just found was this, right? That's this bit. So now we need to find our di, and that is going to be whatever this distance is right here. This distance up to the halfway, which is what we found to be f of xi star divided by 2. So it's going to be times, I'm running out of real estate here. We do x times f of xi star divided by 2. So that gives us our tail end right there, right? So the moment for this particular strip with respect to the x-axis is given by this right here. We can see that this is our mass, right, times our distance away, okay? And if you clean it up a little bit, you get this expression right here. So this right here is going to be the moment for that particular pink strip that I have over on the right. The idea again is if we grab all of these moments and add them up, right, that's going to be the moment for the entire shape with respect to the x-axis. So we have a sum of all the particular smaller moments with respect to the x-axis. Okay? All right. And this is going to be another one that I'm going to highlight in green because we're about to turn this into an integral. Okay? So that is the moment with respect to the x-axis. That's the moment of our shape with respect to the x-axis. Okay, there's one last one to go. And that is the moment with respect to the y-axis now, right? So again, I'm going to go ahead and slap an x and an x and a y-axis down. I'm going to do my same shapes as before. So I'm going to draw my f of x. Okay, let me draw my f of x. And I want it from A to B, right? I'm going to be using the exact same partitions, right? So N. Okay, my exact same partitions, my exact same function f of x. Okay, so now I'm going to find the moments. So I'm going to put this up here. The moments with respect to the y-axis. So now I'm looking at stuff in this direction. I know that sounds confusing. Okay, but just keep in mind that we're looking for stuff with respect to a particular axis, right? Okay, so same shape, at least I tried, from A to B. Okay, so now I'm going to go ahead and do the exact same thing. I'm going to do it based off of here. So I'm going to just go ahead and do rectangle here, rectangle there, and I'm going to make it go this high. I'm not particularly halfway, but there we go. Just a rando point between the two. There we go. So we have our xi plus 1. Let me write that appropriately. So here's our ith rectangle. Okay, we want to find the moment with respect to the y-axis, right? Of this pink sliver right here. It's the same pink sliver from above. It's just, I can't draw the same thing twice. That's it. Don't judge me. I'm not Bob Ross. Sorry. Okay, so the height here is still given by an xi star, right? And since this is an f of xi star will determine its height. Okay, so now I want to find the moment, right, with respect to the y-axis for this particular rectangle, okay? So I'm still going to be doing, I know this is going to be a little bit confusing. I'm still looking for, I'm going to do it over here like this. I'm going to go like that. I'm finding the ith moment, right, for this particular shape, but I'm doing it with respect to the y-axis. So this is still going to be an mi times di, right? It's going to be a moment, or a mass, sorry, equal. Mi times di. So it's going to be a mass times some distance away from the y-axis, right? We know what the mass is for this particular rectangle. We've computed it a bunch of times before, right? So the mass is going to be the rho times basically the area of this rectangle, right? Which is going to be f of xi star times delta x. So just like before, the mass is still given by this thing, right? But now we need to find times di. What is my distance away from the y-axis in this case, right? And this one's actually pretty simple. It is this distance right here. It is from here all the way to here, all the way up to there. And that just so happens to be xi star times xi star. That is the missing distance here, right? So we have this, that our moment for this particular, um, the moment for this particular rectangle here, right, is the mass. I'm going to highlight it just like I did before. It's going to be the mass of that rectangle, right, which is given by the rho times f of xi times delta x, right, times xi star. And look at me go. All of these are missing stars on them. Just make sure you add them in. Okay. That ends up giving us this expression right here, right? So this right here is the moment for this particular rectangle, right? With respect to the y-axis. So the idea here is if we do this for every single rectangle, right, and we just sum up all of the moments, right, we get the moment of this entire shape with respect to the y-axis. Okay, and notice how this is the same breakup from before. Here's our mass. Whoops. Well, these two, three, are our mass, and then this is our distance away from the y-axis, right? Okay, so, and I'm going to highlight this in green. This is our last equation that we need sort of the construction for. This right here is the sum equation, right, for all of the moments of all of the rectangles with respect to the y-axis. Okay, so let me zoom out a little bit so we can grab all three of the equations and take stock of all three of the sort of pictures that we did. Okay, so we have now constructed, let me actually do it with highlight. Okay, I'm going to still highlight it in green though. This is going to be the construction for the total mass of our shape. This right here is the construction for the moments with respect to the x-axis of our shape. And this down here is the moments with respect to the y-axis of our shape. Okay? Now, as I've been doing for the last couple sections from chapter 1 and chapter 2, what we do at this point, right, is we let the partitions from A to B, we let those smaller subintervals, we let those go infinitely small. We just start to shrink them, right? And the way we do that is we let that n go to infinity. We let the number of partitions tend off to infinity, right? And the second we do that, we do an integral, right? That is the definition of taking an integral. Okay. But now, what I wanted to show you guys is you see all three of the equations now, right? And I hope you guys start to see the transition of how, now that we have the constructions, right? We're now going to turn them into integrals, and you guys are going to see how simple it is to sort of formulate the integral themselves, right? So let's go ahead and go down here. Now we're going to do the center of mass, right? Of a thin plate in the XY plane, right? So notice, so suppose R is a region bounded above by a function f of x below the x-axis, below by the x-axis over an interval AB, and let rho be the constant density of this region R, okay? Then the mass, the total mass of our system is this right here, okay? So notice that this is still, if you guys recall the shape, right? It was a rho times f of xi star times delta x, right? And look at what the mass is with an integral, right? There you go. The moments of with respect to the x-axis is given by this thing right here. So if you guys remember that one, right, it was a rho, right, times f of x. Let me write it a little nicer than that. Xi star times delta x times f of xi star divided by 2. That was the construction from our summation, right? And look at what happened here, right? And then likewise for the moments with respect to the y-axis, right? It's this right here. This is, if you guys remember the construction, right? It was a rho times this is the very last one that we did, fxi star times delta x times xi star. And if you rearrange them, right? If you rearrange them and spat out the rho because it's just a constant value, and then took the integral, or sorry, took the n as it goes to infinity, you got this thing, right? Notice how the construction is not too different from the integral, right? And then the last thing now, right, is where the heck is the center of mass? So the center of mass, just this came from the theorem from the beginning of the lecture. It's going to be based on, so the x coordinate is going to be based on the moments with respect to the y-axis, right? And then the y coordinate is going to be based on the moments with respect to the x-axis. Okay, but that's it. Let me highlight the three equations in green. So this is the first one of the three green ones, right? This one is the second one of the three green ones. And this one is the third one of the three green ones. Okay. And notice how the constructions really don't change, right? You can easily tell how it went from the summation version to the integral version. Okay. Okay. That is the construction for finding centers of mass, for finding fulcrum points, right? Or the centroids. That's another word. Okay. Without going too far into the construction here, right? What I want to do is find the center of laminas uh, for a shape bounded by two functions. Okay, and what I mean by that is you have an f of x and a g of x, where the g of x is always less than the f of x, right? I'm going to highlight them in green again, right? The total mass is going to be given by this thing. If you want to go through the construction, you're more than welcome to. It's not too different from what we just did with the equations above, okay? The moments with respect to the x-axis is given by this. Okay, the moments with respect to the y-axis are given by this, right? And then the centers of mass, the x bar, y bar. So the x coordinate is based on the moments with respect to the y-axis, and the center of mass, the y coordinate, is based on the moments with respect to the x-axis. Okay. Just keep your equations straight. I know they swap values back and forth, so just keep an eye out on that. Just keep an eye out on it. Okay. So what I want to do now is an example, and I want to do the example that's based off of the harder one, the one for bounded by two functions. So I'm going to be using these three equations right here. Okay. So here we go. So I want to find the center of mass of the lamina bounded above by the green function and below by the blue function, and my density for everything is going to be 2. Okay. So I'm trying to find the center of mass for this shape right here. Okay, you can go ahead and try to guesstimate. So a shape like this is going to be pretty difficult, right? But if you take a look, right, since all of this, picture, try to picture a point somewhere where we need to balance this thing, right? Maybe like around right here, right? We're thinking because there's so much material up here, maybe some of this material can get balanced out by all of this right here, right? Maybe I can shove it over a little bit, just a little farther, maybe right there. Might be the balancing point. So this is just us guesstimating right now, right? But now let's go ahead and try to figure this out. Cool. So let me actually get rid of that point right there. The first thing I'm going to do is I'm going to the f of x. This is, I mean, it's just to show you guys sort of transformations from pre-calculus, right? Um, but I'm going to try to simplify this. So f of x, right? If I do this out right, I'm going to get minus x minus 1 squared plus 1. I'm going to simplify this out to something a little nicer. And if you do it right, you're going to get minus x squared plus 2x. So I invite you to go ahead and try these out. Okay, try to simplify this out and get this reduced version. Okay, now remember what we need, right? I'm going to write it down over here. We're going to need our mass, our m of x, and our m sub y. So the first one that we have to do, because it's required for both of them, excuse me. The first one that we're going to do, because it's required in both calculations, is the total mass. We're going to find this thing, our m, right? So m, okay, is we need to find the mass of this thing, right? Now, we can see our limits of integration. If you take a look, right, it's going to be from the 0 point to this point way over here, which is 2.5, right? So that's going to be, so the equation here is going to be, I'm going to follow it from right up above. I'm going to be using this first green one, right? Rho times the integral from 0 to 2.5 of f of x minus g of x. So my f of x, we know what that is. I reduced it down to this, right? So minus x squared plus 2x minus my g of x minus 1/2 x. So when you do this, when you do the arithmetic, when you do the algebra here, and this is dx here, make sure the equation in itself has a negative, right? The equation for the mass has a negative in and of itself. And your g of x also has a negative. So make sure you separate those two away, right? So this is going to be equal to, let me actually, maybe be smart about it. I'm going to go ahead and grab all of that, move it over so that I can write down my equation. So it's going to be a rho, right, times the integral from a to b of my f of x minus g of x dx. Whoa. Okay. Okay, we've got everything we need. So now let's go ahead and compute this out, right? This is going to be equal to rho times the integral from 0 to 2.5 of, if we reduce all of this down, minus x squared plus 5/2 x dx, okay, which is equal to rho times negative x third over 3 plus 5 over 2 x squared over 2 evaluated from 0 to 2.5. And if you do this appropriately, I'm going to compute it out. Rho we know is 2 minus 2.5 cubed over 3 plus 5, 2.5 squared over 4. All of this is equal to 5.20833 repeating. Okay, so we have our final mass, right? Our total mass for our shape. All right. So now I'm going to move down here. I'm giving myself a lot of room here to work. Okay. You should do the same thing because these computations tend to take a lot of space. Unfortunately, welcome to Calc 2. If you haven't done a calculation that's 2.5 pages yet, you're not doing it right. So mx, we're going to go ahead and find mx first. So we're finding the moments with respect to the x-axis, right? And the equation for this one, right? Let's go up above here, is this one, the one with the minus squares, right? So I'm going to go ahead and rewrite that equation. Rho integral from a to b, right, of f of x quantity squared minus g of x quantity squared all over 2 dx. Okay. Again, don't mess up on the calculation, right? The equation in itself has a negative, and your g of x in this case has a negative. So you have to make sure you're handling both at the same time. So equal to rho 0 to 2.5 minus x squared minus 2x squared minus 1/2 x squared all over 2 dx. Okay, I'm going to go ahead and solve a little bit more. Rho 2.5, you're going to have here, all of this is going to reduce down to let me get this right. Yeah, x to the 4th minus 4x cubed plus 4x squared minus 1/4 x squared all on the top divided by 2 dx. Okay, and if you do this right, if you compute this all out right, I'm going to put one more set of answers here. So it's a divided by 2, rho is 2, so all of this computed out will be this. X to the 5th over 5 minus x to the 4th plus 4/3 x cubed minus x third over 12, evaluated from 0 to 2.5. And this, if you compute it out right, is going to be 0. So just watch it, watch your signs when you do this, okay? That is where usually, for calculus students, your calculus is immaculate. It's your algebra and your arithmetic that sucks. So double check your signs, double check your negatives, double check your values, double check whatever you're plugging in, make sure all the decimal points are where they're supposed to be, okay? Okay, so this is m sub x, right? The moment with respect to the x-axis. Now I'm going to find the moment with respect to the y-axis. And that is equal to rho times the integral, right? From a to b. I'm just writing the equation over again of x times f of x minus g of x dx. Okay, off to the races. Rho 0 to 2.5 of x times f of x minus g of x. So it's going to be minus x squared plus 2x minus a minus 1/2 x d. Let me make that in actual parentheses there. Dx. Okay. And this is going to become, I'm going to multiply the x in. So it's going to be rho times the integral 2.5 minus x cubed plus 2x squared plus 1/2 x squared. You put parentheses here, dx. Here I'm going to go ahead and add in my rho. So it's going to be 2 times negative x to the 4th over 4 plus 2 x cubed over 3 plus 1/2 x cubed over 3 evaluated at 0 and 2.5. And if you do this part right, you should get something along the lines of 6.5104. And I think the 4 continues to repeat. Sorry, 4333. And the 3's continue to repeat. Wait, nope, wrong. 166. The 6 continued to repeat. There we go. Whew. Okay, so we have our total mass, our moments with respect to the x-axis, and the moments with respect to the y-axis. So now I get to compute the last bits. So the y bar is what requires the mx over m, right? Our mx is 0 over our total mass, which was 5.20833 bar, right? And this is just going to be 0. Okay, and then our x bar, that required our m sub y, so m sub y over total mass, 6.510466 bar over our total mass, which was 5.20833 bar. And if you do this right, you get 1.25. So our center of mass, our balancing point, our fulcrum for our shape needs to be placed at 1.25, 0. That's where we need to place our little fulcrum point. That's where we need to place our finger. That's where we need to put the pencil in order for this shape to balance out. Okay, so it's going to be 1.25, 0. So 1.25, that's a quarter right there, about. So in order for this thing to balance, we have to put our pencil right there at that particular spot. Oh, give me go. This is 1.25. So this is 1.5. 0.25 is a quarter. So about right there. Haha. Oopsies. Read your graphs. Make sure you read your graphs appropriately. So there you go. That is the full-fledged work for finding the centroid of something. Okay, finding the center of mass for something. Okay. So make sure you go through every step. Okay. Make sure you understand every step. Okay. These are long problems. Okay. And as always, right, I do expect everyone to be able to compute every single step in here. Okay. For the arithmetic portion. So when you actually have to compute, let's say this part right here, right? I expect you to be able to compute it, right? This part as well. Make sure you're able to compute it. You can double check your answer using the definite integral calculator. Okay. So don't be afraid to use the definite interval calculator to make sure that your numbers are correct. Okay. All right. What comes up next is one more quick check. There's going to be two shapes here. Okay. They look similar, but they're not. Okay. And I forgot to put, I think this one's from uh, 0 to 4. Okay. The shapes look like they're similar, but they're not. Okay. Graph them and you'll see what I'm talking about. Okay. And I believe that is it. I think the next part are lecture questions. Make sure you, if you have trouble with any of this stuff, we're getting into the harder stuff. Okay. If you have any trouble with any of this stuff, come visit me in my office hours. I have Friday hours, or just, flatly just shoot me an email. Tell me how to, that you're stuck on a spot and we'll figure out a time. Okay. Besides that, I think I'm done here. Happy studying.